Hi there and welcome to the very first video about circuit. In this video, we're just going to give you an overview, a very broad general overview about what circuits are and what they are made of. So let's crack on. I'm going to take a slightly different start in the sense that I'm not going to draw a circuit at the very beginning uh, just because there's some bases that I gotta give you. Probably you have already been taking chemistry and physics classes, uh, but if you're new, don't worry about that. So, generally, what is a circuit? Whenever you have a closed loop and you have some differential potential, uh, electrons are gonna flow from one end to the other. We're basically gonna, in an atom, we're basically gonna have protons and neutrons at the center because protons are way bigger than electrons, and then electrons, rotating with a spin around the center, the nucleus of the atom. Well, actually, there are also um, other particles that are actually smaller, which are called quarks. But I'm not gonna be talking about quarks in this case. They're fractional, but you can just see video about quarks if you're interested. But I'm not gonna be talking about quarks in this video. So um, if we have, let's just take a broad view. Um, let's just say that we have a copper, so a copper wire. So the wire that are also in your house and so on are made out of copper. And copper has the nucleus here, which I'm just gonna draw with all the neutrons and protons. And then we're gonna have the energetic levels out here. The first, the second, the third, and the fourth. So the second. Then we have the third. And then we have the fourth one. Then we're gonna have two electrons in the first one, which is complete. Then we're gonna have 1, 2, 3, 4, 5, 6, 7, and 8 electrons in the second one. And then we're gonna have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18 in the third one. And then we're just gonna have one electron in the fourth one. So as recap, in the first level, we have 2 out of 2. In the second level, we're gonna have 8 out of 8. In the third level, we're gonna have 18 out of 18. And in the fourth level, we're gonna only have 1. Now, the thing is that each and every level can have a maximum of a certain amount of electrons. So the first level is complete, the second level is complete, the third level is complete, but the fourth is not, and it only has 1 electron. Now, each and every element is actually trying to complete its electronic level. So copper doesn't actually kind of like this little electron here, so it's actually easy for this electron to, you know, move. So if you actually bring it close to another element, the electron is actually gonna move. And if you actually bring it close to another copper, in a copper wire, two of those are gonna exchange this electron. The thing is that when two of those actually exchange an electron, uh, the, this whole thing is going to be left with one electron less, and the other one with one more electron. So this one is like as if it becomes positively charged, because you know it's losing a negative charge. Remember, all the elements in this case, this atom here, it's neutral, which basically means that it has as many electrons as the protons, so it's neutral. Now, if we can force, like apply a differential potential some way, somehow, and make those electrons, so these electrons here in the upper level, in the fourth level, move in a certain direction that we want, we're actually going to have current. Because, you know, if we just, you know, exchanging this electron with another atom of copper, it's not in a random direction and moving in a random direction like so, it's not going to be useful. It's not going to, you know, be useful for our purpose. So if we imagine actually a copper wire, in a copper wire, I'm just gonna draw it like very simply. Let's just pretend that we only have this upper level, okay? Like this is the nucleus of those atoms, okay? This is a copper wire, and we have this tiny electron in the upper level. So it's actually moving, but it's moving in a random direction, okay? It can exchange this one with this one, and then this one perhaps with this one, and this one perhaps back to this one, and so on. This doesn't actually, you know, produce anything useful. But if we can, you know, instead of this, like force each and every one of them to move in a certain direction, then we're gonna have current. So current is actually the flow of electrons. So now in a circuit, we're gonna have a few elements. The very basic and very simple circuit is just gonna be made of a generator with a plus minus and a resistor. Sometimes you can also see the generator like this, and the resistor still like this. And it doesn't matter. This one only stands, is a very same notation, just stands that the bigger part here, the bigger line here is positive, and the lower one is negative. And this is the resistance R. Generator generally a difference of potential. So what happens? Well, let's suppose that we just wrote positive and negative, so positive and negative, and we're going to say, okay, the current is going to flow this way, and the current is going to be called I. And I know what you're thinking. You're just saying, hold on a second. If the current, you know, if we're making the current go in one way, and current is like, you know, the flow of electrons, then why doesn't it go from negative to positive, like from here to here? Well, it does. It actually does, because it's the electron that are moving, and by moving, they're basically leaving the positive charge there, because those are negatively charged. And protons don't actually move because they're very, very heavy. Although in computer science, engineering, and electrical engineering in general, we're actually saying that for a convention, in order not to have negative signs popping up everywhere, we're just saying, okay, the current is flowing from positive to negative, like so. So, what is actually going on in this case is that from our source, so like our generator, a current is, there is a difference of potential, and a current is flowing and getting back here, flowing and getting back here. So we know what this generator does. It just it has a certain voltage in volts, and is actually saying, okay, I have, I don't know, like 10, 12 volts and so on, and I'm just pushing. And just volt is like saying, okay, I'm pushing this current through this wire. Now, as the current actually gets to the resistor, what the resistor does is that it just, well, a resistance that opposes the flow of current. So, in order to better explain what a resistor does, I'm gonna introduce the concept of isotropic and anti-isotropic materials. What does those means? What do they mean? I mean, those words. What do they mean? Those two words, which just like just one but combined. Well, isotropic means that an element, like something, even this piece of paper, is regular. Now, this piece of paper is not regular, of course, but isotropic just means that it's like a crystalline, is like crystal, like it's regular everywhere. Whenever you move in the X, Y, and Z direction, you're always gonna find the same thing. Whereas anti-isotropic, and most of the things are anti-isotropic, don't have this property. Like it matters if you move along the X, Y, or Z axis, because you're not gonna find the very same thing everywhere. And why? You're basically thinking, why did you want to introduce those two things? Well, because as we said, there is a current I that is going through the resistor, and the resistor is basically just something that opposes the flow of current. How does it oppose the flow of current? Well, if we are going to zoom in, okay, is just zooming into the resistor, okay, the resistor is actually going to have something, some atoms here made of something, because the resistor is actually made of something. There are atoms in there, like so. Everything is made out of atoms, Okay. So those are the atoms of the resistor. So now, if we have this difference of potential, so those electrons going in this direction, okay, they're gonna move, and get into our resistor. Uh, but here is what happens. Those things here are not gonna be, transparent, like in the sense that you can get through them. No. You're gonna have a totally unelastic crash. So basically, those electrons are just gonna crash on the nucleus of those atoms, and it's gonna be totally unelastic, which basically means that the velocity, if we have to plot this into a graph, we will have the velocity of the current flowing will be like this and then down, like this and then down, like this and then down, like this and then down. But we can actually average it like so, like this, because we know that the velocity, actually the speed at which the electrons are of the current are entering a certain resistance is the same as the one in which they are going out. So we can actually, for the sake of simplicity, just average it and consider it like this. But the resistance is just opposing to the flow of current. Now, when they heat the nucleus, they heat it at a certain speed. So they're basically losing their speed for these because they're hearting those. And then they gain it again and they heart something else like this one, and then they gain it again and they heart this one, and they gain it again and they heart this one, and lastly they manage to get out. But each and every time they heart a nucleus, they're basically going to lose a little bit of energy, and this energy, since nothing is just lost like this, this energy is actually transformed into heat, which is why the resistance is actually gonna heat up. For instance, if you look at I'm pretty sure you do have, like in the bathroom, well, in the restroom actually, or in your bathroom and so on, something like, I don't know, something to warm up, like, I don't know, could be anything, like even your hair dryer. The hair dryer actually has a fan at the basically at the very bottom that is actually pushing air into this into the air dryer itself, and within the air dryer there are just resistances, and those resistances are gonna heat up, and the air is gonna go through those resistances and go out from the air dryer, and therefore you can just use your hair dryer, which is basically what happens. So you basically have current flowing in, warming up those resistances. Those resistances are warm up because there are all those unelastic, totally unelastic, those electrons flowing and hearting the nucleus, and this is basically why they're gonna release energy in the form of joule, well, actually joules, according to the pronunciation. I never got it right anyway. So let's just stick with joules. So they're gonna release energy in the form of joules, which basically means that they're gonna heat up. So this is a very basic circuit. Now, I'm pretty sure that you're familiar with volts, but you might not familiar with ohm. So basically, a battery or a power supply, could be anything, is measured in volts, and resistance is measured in ohm. The current flowing instead, which we call I, is measured in ampere. And in can actually be a good time to introduce first law, which basically says V equal to R times I. You can actually memorize it by saying, okay, let's just draw a triangle with V, I, R, and just, well, this is going to be a triangle. Okay. And you can say, okay, I gotta find V. So V is equal to I times R. I gotta find I. I is equal to V divided by R. I gotta find R. R is equal to V divided by I, and so on. But you can also memorize this one and get all the others from this one only. So let's do something very simple. Let's suppose that we have a 12-volt battery over here, and a 0.5 ohm resistance over here. Then the current I is going to be, remember, V divided by R. So we will basically have V divided by R. So I will be 12 divided by 0.5. And this is basically our current. So this is pretty much it. I hope this gives you a very brief and general overview about circuits. And wait for part 2.